In the earlier video, we spoke about the different forms of energy. We specifically looked into the two components of mechanical energy, which was the potential energy and the kinetic energy. And we also touched upon the law of conservation of energy, which stated that in an isolated system, an energy can neither be created nor destroyed, but it can only be transformed from one form to the other. And while solving some of the in-text exercise problems, we did see that we did come across scenarios where mechanical energy was getting converted into sound energy, like the scenario of an iron ball or a huge object falling on the earth, wherein the kinetic energy eventually gets transformed into a sound energy, right? And we hear a huge thud. And the signs of sound energy is what is going to be our focus in this specific video and possibly the next video. And this video or this chapter about sound is relatively a bit theoretical, unlike all the other chapters of physics that we learned, right, as part of the class 9 syllabus. So this one is a little theoretical, but nevertheless it's as interesting as the other chapters. Conceptually, it's very interesting as the other chapters. So let's get started. Okay. So let's start with how is sound generated? What is the source of sound? We saw that we hear the sound when a large object falls onto the ground. That is one way, right, wherein mechanical energy gets transformed into sound energy. But take the scenarios of the sources of sound around us, right? Say look at the scenario of a guitar, a string, right? How does the sound emerge from that? I mean, you pluck the string and there is sound, right? And flapping of wings of birds, that creates sounds. When you clap your hands, that creates sound. You have a rubber band and you stretch that, you plug that, you hold it tight, and then you plug that, you get sound. So if you observe closely, the source of sound is vibration. An object vibrates, and that's how sound is generated or sound is created around that, right? So vibration is there is a disturbance on that of that object in the form of a vibration, and that becomes a source of sound energy. Now, if vibration, so let's take the example of a guitar string, and you plug that guitar string, the string vibrates, and that vibration generates sound or creates sound. Now, how do we hear it? Now, there has to be a way for the sound to propagate from the guitar string all the way up until our ears, right? Unless that happens, we cannot hear. So sound has to propagate. A vibration of an object generates sound, and that sound has to propagate to our ears for us to be able to hear that and perceive that sound, right? Which means that sound needs a medium to travel. And we'll quickly get into how sound propagates. But in a sense, between the guitar and you, for us to hear the sound of the guitar, we need the sound has to travel through a medium, and that medium can be air is a good medium for sound to travel, and sound can also travel in a solid object or in a liquid object too, or in a gaseous object too. But sound needs a medium to propagate and then reach your ears, and so that you can perceive that there is sound, right? And how does sound propagate? Again, just the way it is generated from vibration of an object, sound is propagated by vibrating the particles nearby, right? So, if I take an example of take the example of a tuning fork, right? It looks something like this. Let's take the example of a tuning fork, and let's say we strike it, and so that there is vibration, and let's say you're here, right? Let's say you're here, And for you to hear the sound created by the tuning fork through its vibration, it has to propagate through the air, right? So it has to cover the distance and reach your ears. Only then you can perceive sound. Now the tuning fork is vibrating, which means that it pushes the air and then it comes back. It pushes the air and it comes back. That's how an object vibrates, right? So what happens when an object keeps moving back and forth? It keeps pushing the particles nearby, no, not continuously, but it leaves a gap, right? It pushes, it comes back. It pushes, it comes back, right? So what will happen is as the object vibrates, the object is also likely going to create a it's going to vibrate the result of the vibration of the tuning fork is going to cause the nearby air particles also to vibrate, right? And that the fact that the air particles vibrate is also going to is going to cause the vibration of the even nearby air particles, and that's how the sound propagates, right, through the medium. So the vibration on the tuning fork is causes the air particles to vibrate, and air particles causes the other air particles to vibrate, and that's how it moves, and then it reaches your ears, right? So when you really when you really see this, that vibration that you see here is going to have a pattern, right? Because it pushes, it comes back, it pushes, it comes back. So which means that the vibration is also going to alternate, right? So once an object when it pushes, it's going to have a high, the pressure is going to be high on the particles nearby, but when it comes back, the pressure is going to be low. Then once again the pressure is going to be high, and then the pressure is going to be low, right? So that is how that is how the vibrations are going to propagate from the tuning fork onto the air particles. So if you think about it, the vibration of the tuning fork through its alternate motion, to and fro motion, is going to cause a variation in pressure on the nearby particles, or it can also be a variation in the density of the particles, right, between in the line of propagation. So what I mean by that is when it pushes, the pressure is suddenly high on the air particles nearby, and which means that a lot of air particles are there. But when it comes back, the pressure is low because nothing there is no pressure exerted. Now once again, if it pushes in, so you're going to have some more high density air particles and high pressure, and then when it comes back, it is going to be once again low, right? So that is how the air particles keeps, that is how the vibration is propagated all the way through the air particles until it reaches your ears. So if you visualize this, it's going to look like that change in pressure, or that change in the density of air particles is going to be somewhat like this. It's going to alternate, right? As long as the tuning fork vibrates, you're going to have the air particles nearby is going to have sequences of high density pressure or high density air particles and low density pressure or low density air particles. So it's going to be alternating pressure variations or density variations, right? A vibrating tuning fork is going to create an alternating pressure variation or the variation in the density of the particles part of the medium. The medium is air in this case, and that is how sound is propagated. And as long as it reaches your ears, this pressure density, this variation, as long as that reaches your ears, you will be able to perceive the sound of the tuning fork, right? So this is how sound is generated. Primarily, it is generated from the vibration of an object, and it is propagated through the vibration of the particles that are part of the medium, right? And just to if you really visualize this, if you were to plot this behavior of a tuning fork and the vibration of the nearby particles, or the alternating variations in pressure or density of the tuning fork, of the vibrations caused by the tuning fork, you can plot a graph something like this, right? If your x-axis is going to be your distance from the tuning fork, and your y-axis is going to be the strength of pressure or density, right, of the air particles. If this is how if this is a graph that you've considered. So at this point, so the way we can plot the behavior of the tuning fork during vibration is there is a high pressure, there is a low pressure, right, and there is a high pressure and then it comes down, right. So it keeps alternating, right. So so if you really plot this behavior, there is an area of high density or high pressure which is here, and there is then it slowly comes down, and it goes. I mean, this is what is equilibrium, the state where the object is neither pushed nor pulled, right? An air particle that is neither pushed nor pulled, that is your normal equilibrium, right? And this vibration pretty much causes the objects to be completely pushed, or it gets completely pulled back, right? And that is how this whole variation, this synchronized variation of pressure or density is left on the air particles. So if you really plot this into a graph, plot this behavior into a graph, it's going to look something like this, where your pressure or density is going to start with a high positive, and which is a push, right? It's a push, and then by the time it comes back, it becomes a complete pull, and it goes through the equilibrium, comes back to its maximum pull, and then once again it pushes in, and then it comes back, and so on, right? So this is how the sound wave, and this is what we call as a sound wave, and this is because the behavior can be, when you plot the behavior of sound on a graph, it looks like a wave, and that's how we call it a sound wave. So one other interesting thing is we spoke about the importance of medium, and because sound the vibration needs to disrupt or vibrate the nearby particles, and that vibration will in turn disrupt the nearby particles, and so on, and that's how the sound wave propagates. And if that vibration reaches our ears, we can hear, right? So sound needs a medium to propagate. What if there is no medium? Sound will not propagate. I mean, which means that if in a scenario where between you and the tuning fork, if there is no air particles, if there is no liquid nor gas nor anything, right, and if it is complete vacuum, which means that sound will not propagate at all. And you can try that out. There is an experiment wherein when you keep a cycle bell or an electric bell inside a jar, and if you suck all the air out of that jar, so let's consider this is your jar, and it's closed on the top, and let's say that you have a bell or something, which means that you have a bell or something which keeps hitting it, and as long as there is some air inside the as long as there is some so this is your bell, right? So this is your bell, and let's take that this is sealed originally, and then as long as there is some air particles nearby, and you switch on the bell, you will be able to hear it from outside. But as you repeat this experiment by sucking out all the air, right? When you suck all the air from the jar, and then when you start ringing the bell, you will observe that the sound becomes feeble, less feeble, and then so on. And when you completely take all the air out, when it is complete vacuum inside the jar, you'll not be able to hear the sound at all. So which means that for the sound to reach from this point to the end, right, it needs a medium. And when there is when there is absolute vacuum, the sound that is generated, although this object vibrates, and this is not going to reach the edge of the surface of the jar. So this is an interesting experiment you can try out, and this will this is something that will prove that sound needs a medium to actually propagate. So now that we have seen that the sound is a wave. Why we call it a sound wave? Because the alternating pressure variations when plotted on a graph, right, it becomes a wave. It shows up like a wave when you plot that against distance, right? So there are other forms of waves too, right? We will learn in the further chapters and all that. Light energy is also a wave. Light is also a wave, and in fact, light is special. It is both a wave and a particle, but nevertheless, it is a wave. But is that a wave, light wave, very similar to? We can also light helps us see things the way a sound helps us hear vibrations, right? But are these waves exactly the same? Though we call them waves, are light waves and sound waves exactly the same? No, not really. There are both of them are waves, but the way they propagate is slightly different. In fact, it's quite different, and that's what we're going to quickly see. So we'll see for sound waves. Let's see. In the case of sound waves, you have, I'm going to use a different color. So let's say, you have a tuning fork here like this, and this is starting to vibrate, and which means that it is going to vibrate the nearby air particles, right? So let's assume that, these are the air particles that are nearby, right? And how does the sound propagate, right? When the tuning fork starts to vibrate between left and right, so it moves between left and right, which means that it is going to apply a pressure on these two directions on all the particles nearby, right? Every particle is going to have a push and a pull on the left and right hand side directions, right? So this is how the pressure is going to be applied on this. So if I'm going to just zoom it, so let me just to make it very clear. So let me phase this pretty well. So if this is how the particles are nearby, so your sound wave propagates. The pressure is applied in like this, right, on all the particles nearby. That is how the vibration felt by the tuning fork is propagated onto the air particles. It pushes, it pulls. It pushes, it pulls. And the push and pull on this particle is applied on the subsequent particle, which in turn is applied on the subsequent particle, and so on, right? So this is how the sound is propagated. If you really see a light wave doesn't really propagate like this, although we call it a wave. A light wave pretty much propagates like the way like the way the waves in water are formed. So if you really drop on a sea, if you drop on a surface of water, if you drop a stone, right? If you drop a stone, what happens? You will form waves like this, right? Which means the surface of the water that was plane, or that was a straight line, upon once you drop an object on it, some parts of it goes up and goes down, right? Every water particle on the surface, it goes up or goes down, and it repeats it, right? And that is how waves are formed, and that is how light wave also propagates. So in essence, light wave propagates like this. Light wave propagates. Every cell goes up and down, and it goes up and down. And it goes, it's not every cell, every particle goes up and down, and so on. And that is how, light waves or water waves are formed, right? So there is a difference you might notice, right? So this is how sound waves are formed, and this is how, water or, light waves are propagated. So I hope this difference in propagation is clear. So what we call these are as we call these objects that go back and forth these we call waves that propagate back and forth in the line of the direction of the wave, right? So in this case, the propagation of the wave is this, right? This is how the wave is propagated. The sound wave is propagated. But in this case, the wave is propagated this way also, right? In the case of light and water, the wave is still propagated this way, but the direction of the particles are perpendicular to the direction of the propagation of the light wave or the water wave here. But in this case, the direction of the particles the direction of the particles are parallel to the direction of the propagation of the wave. So this difference, and we have a name for that, and we call these waves which move, where particles move parallel to the propagation of the actual wave, which is example of sound. We call these waves as longitudinal waves. And scenarios like water and light, where the particles move up and down, they move perpendicular to the propagation of the wave, we call those waves as transverse waves. So sound is a longitudinal wave, and light, water, they are transverse waves. So I think we'll stop here, and we'll go over the other aspects. In the next video, we will talk about the various aspects of sound wave, and we'll possibly get to know some formulas, and we'll use them for our problems in our exercises.
One final thing before you leave. If you wish to revise the concepts that you've just learned, please look up and try out the free Revise app bot on Telegram app. Telegram is available for free on both iPhone and Android. Also, if you did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.